Here's another kinematics problem which requires us to make use of calculus. So once again, this may not be the kind of problem that you will see if you study kinematics for the first time in school, but it might be something that you'll get either as a high school student doing Olympiad, or you might get this as a first year student in uni if you're doing some form of engineering like aerospace, mechanical, civil, or anything like that. So in this particular question, we are dealing with a graph which shows velocity against distance. And what we're being told is that the velocity is um, decreasing with distance, and it decreases along this straight line, right? So the shape of the graph is a straight line, which automatically means that we can write v as a function of s as, I guess, a. Actually, I won't use a because we can use a for acceleration. I'll use cs plus d, where this is going to be the slope of the graph and this is going to be the y-intercept. So we already know what the y-intercept is because it's on the diagram. So that's going to be 20 meters per second. So it's this value right here. That's where it crosses the y-axis. So this velocity decreases from 20 meters per second, and it says to a value approaching zero at the displacement of 30 meters. So what we have to do in this particular question is we have to find the acceleration of the particle when the displacement is 15 meters from, well, when the displacement is 15 meters. So that's the first thing. And the second thing is to show that the particle never actually reaches this point. So we'll think how to do that after we go beyond the first part. But let's try to, first of all, find the slope, and then we'll try to find the acceleration at that particular location. So one thing you might notice is that this 15 meter is between 0 and 30, right? Which means that you can find the velocity if you want. So you've got a velocity of half of that, so that would be 10, right? Because 15 is like halfway between 0 and 30, then this value is going to be halfway between 0 and 20, which is going to be 10. Now, that's the velocity at this point, but it still doesn't really tell us what happens to the acceleration. So we have to use a bit of calculus to figure that one out. Now, in terms of the velocity itself, I think it's a good idea to try to find the slope at first. So I'm going to rewrite this as v as a function of s is going to be equal to c times s plus 20. So that's the equation for the velocity as a function of distance. And we can also notice that according to this line, when the displacement is 30, the velocity is 0. So we can write this as 0 is equal to c times 30 plus 20, which means that c is going to be equal to minus 2/3. So we can write this velocity as a function of s as 20 minus 2/3 of s. So this is how the velocity changes with displacement. Now, in order to find the acceleration, what we can do is we can straight away differentiate this equation. So we can say that v is 20 minus 2/3 of s. And if we differentiate it, obviously we have to differentiate both sides. So I'm going to do dv by dt is going to be equal to d by dt of 20 minus 2/3 of s. So let's take this to the next page and let's see what this is going to give us. So obviously dv by dt is acceleration, and then the d by dt of 20 is 0, and then minus 2/3 ds by dt is going to be just the velocity. So we can say that acceleration is minus 2/3 of v. Okay, so we can actually use the graph to figure out that the velocity is going to be 10 at 15 meters based on geometry. So if we replace the velocity with that value, which is 10, then this will be minus 20 over 3. And you can leave it like that if you want, or you can calculate the fraction, and this is going to be equal to minus 6 point, I don't know, 6 recurring meters per second squared. So that's the acceleration or the deceleration rather. And you can actually tell straight away that this object is decelerating because its velocity decreases all the time. Now, the second part of the question is asking us to look at the fact that the particle never reaches the 30-meter displacement. So what I would do in this case is I would use the original equation for velocity. So let's take this one and let's do some things to it. So for example, let's write the velocity as the first derivative of displacement like this. So I'm going to have ds over dt will be equal to 20 minus 2/3 s. So we can then separate the variables and then integrate. So that's going to give us ds over 20 minus 2/3 s is equal to dt. And we're going to integrate both sides. Now, you can use substitution, but I won't bother with doing substitution. I'll just rearrange the, the left-hand side to be able to integrate it straight away. So what I'll do is I'll put a minus in front, and then we have the integral of ds over 2/3 s minus 20 is equal to t plus a constant. And then another thing I will do is I'll put a 2/3 on top, and I'll multiply this with 3/2 on this side so they cancel out, which is going to give me minus 3/2. And then the numerator, if you look at it, actually this 2/3, right? I'm going to rewrite this 2/3 as the first derivative of the denominator. So it's 2/3 s minus 20 prime over 2/3 s minus 20 ds, and this is t plus a constant. And this is going to give us minus 3 over 2. And then this integral is just the natural log of the absolute value of 2/3 s minus 20. And this is equal to t plus a constant. So let's see what we end up with if I move this to the next page. Now, this absolute value is obviously a positive quantity, but the thing inside the absolute value, this 2/3 s minus 20, this is negative if you look at the diagram, because s starts from 0 and it ends up as well, it can end up as 30 depending on how the particle behaves, but we're predicting that it never actually reaches that point. So because 2/3 s minus 20 is less than 0 or less than or equal to 0, we can actually say that the absolute value is actually 20 minus 2/3 s. So I'm going to rewrite this like that. So this is minus 3 over 2 natural log of 20 minus 2/3 s, and this is equal to t plus a constant. Now, we're going to try to find the constant of integration by saying that at the initial time, the distance is 0. So this is going to give us that minus 3 over 2 natural log of 20 is equal to c, like this. So let's put everything in. We have minus 3 over 2 ln of 20 minus 2/3 s is equal to t minus 3 over 2 ln of 20. So let's try to maybe get let's try to get time actually instead of distance as the subject. So we're gonna try to isolate time, and time is gonna be 3 over 2, and then we're gonna have ln of 20 minus ln of 20 minus 2/3 s, like this. And if we use the log properties, this is the same as 3 over 2 ln of 20 divided by 20 minus 2/3 s. Okay, so this is what we ended up with. So this is kind of a function of time with respect to displacement, because the function, sorry, the problem is asking us to show that the particle never reaches this 30-meter displacement. So let's see what happens if we sub in the value of s equals 30, right? Because this should give us the time until the particle reaches 30 meters. So if we put s equals 30 here, this is going to be ln of 20 over 20 minus, so this is 2/3 times 30. And this is 10, this is 20 minus 20. So yeah, we just get ln of 20 over 0, which is not defined, right? So what we can do instead is we can take this to the limit. So I'm going to cross this out. And we're going to say that the limit of t for s approaching 30, but s being less than 30, right? So this is important because obviously s starts from 0 and it creeps out towards 30. This limit is equal to the limit for s approaching 30 from the left-hand side, so s less than 30, of 3 over 2. And then you have ln of 20 over 20 minus 2/3 of s. Now, if we put in the value, obviously we don't get anything that's mathematically meaningful because we can't divide by 0, but we can take the limit, and this limit is going to turn into 3 over 2, and this is going to be ln of 20 over, and this is something that I like to call like a positive 0, right? Which means it's essentially the limit is 0, but it's positive. And the reason it's positive is because s is approaching 30 from the left-hand side, right? And we know that this limit is infinity, so the whole thing is infinite. So this means that the time it takes for the particle to reach 30 meters is infinity. In other words, it will never reach 30 meters. And the reason for that, from a physical point of view, is because technically the velocity decreases until that point. So it will slow down so much that it will, at some point, it will start just creeping towards 30, and it will never be able to reach it as a result. This is kind of similar to that other problem, which is completely unrelated to physics, but that problem is related to a snail, which moves, let's say, in the first day, it moves 1 meter, and then it's essentially trying to reach its goal, which is 2 meters away, right? And in the first day, it moves 1 meter. In the second day, it moves half a meter. In the third day, it moves a quarter of a meter, and so on. And this snail will actually never reach the 2-meter mark, right? Because its velocity will converge asymptotically to 0 every day. So eventually, the velocity will converge to 0, and the time until it reaches 2 meters will be infinite. And this is what happens in this case as well. And that's the end of the question.